Hello everyone, welcome and thank you for joining us for DigitalGlobe's lead webinar series, Learn, Engage, Act, and Discover. My name is Becky Schneider and I'm the Marketing Programs Manager at DigitalGlobe. Before we get started, here's a few tips to keep in mind while viewing today's webinar presentation. All attendees are on mute, so to ask a question, please use the Q&A chat box feature that's located at the right-hand side of your screen. All questions will be answered at the end of today's webinar. A link to today's webinar recording will be sent to everyone via email within the next 24 hours. Today's webinar, titled The Importance of Surface Reflectance for the Analyst of Optical Very High Spatial Resolution Images, will illustrate that not only surface reflectance is necessary to consistently and efficiently analyze satellite imagery, but also that the angular information of the acquisition should not be neglected, as it can provide unique features on the scenes being analyzed. Today's webinar will be presented by DigitalGlobe staff research and development scientist, Dr. Fabio Pacifici. Fabio has been with DigitalGlobe since 2009, and he received his PhD from Tor Vergata University in Rome, Italy. Prior to joining DigitalGlobe, he collaborated as a visitor scientist with the Department of Aerospace Engineering Sciences at the University of Colorado in Boulder, and he has been involved with various remote sensing projects supported by the European Space Agency. So without further ado, I would like to welcome Fabio, and let's begin today's webinar.
Thanks, Becky. Hello, everyone. Welcome to this webinar. Today I would like to discuss with you the importance of surface reflectance for the analysis of very high spatial resolution images. This is the agenda. We'll go through some introduction and explain what is surface reflectance, and I will go through some application, including change detection, lens cover classification. Then I will discuss some current technology to compensate the images for atmospheric effects, and after that I will be showing some additional examples. So the first question I would like to answer is, what is surface reflectance? So surface reflectance is the physically based normalization of the image values regardless of the different atmospheric and viewing condition. So that means that it corrects the images to be consistent with the viewing the area from the ground. In this figure, what you see are the quantities that are available during an image acquisition. In particular, the sensor measures the photoelectric signal that are proportional to the radiance reflected by the Earth when illuminated by the sun. We generally don't have access to this electric signal, as those are directly stored in the image via digital numbers. So digital number is a quantity that is not physically based. It depends on a bunch of factors, generally operational settings such as compression level, pixel aggregation, line rate, bit depth, and TDI, which stands for time delay integration, which is a sort of exposure of the camera, and also seasonality. So this means that digital number data should not be compared to digital numbers from other satellites, nor from the same sensor. And this is because the operational settings or the atmospheric conditions may be completely different. A better normalization of the data can be achieved using physical quantities. The first one that I will illustrate is at sensor radiance. At sensor radiance can be calculated based on these formulations once we have the knowledge of the gain and offset. And usually these coefficients are stored in the image metadata. So once you have access to the image metadata and the digital number, you can retrieve the radiance. An additional reduction in scene-to-scene variability can be achieved using top of the atmosphere reflectance or at sensor reflectance. What we can see here by this formulation, we account for the radiance, but also for the illumination conditions, in particular the solar irradiance and the distance between the Earth and the Sun, and also for the solar zenith angle. So that means that basically we are correcting the image or compensating the images for the different illumination conditions. An additional step in reducing the scene-to-scene variability can be achieved by using surface reflectance. Surface reflectance can be calculated using more complicated formulas, such as the one shown in the figure. What is important to see is that we can see elements from the previous quantities, in particular the radiance, the solar irradiance, and the distance between the Earth and the Sun, but also some new components such as the upwelling radiance. And I want to spend a little bit more time describing what is the upwelling radiance. So this is one of the major components of atmospheric spectral distortion. It is driven by Rayleigh scattering. It has an effect as a lambda powers of -4 dependence with the wavelength. That means that shorter wavelengths, such as coastal or blue band, are more affected by Rayleigh scattering than other bands, such as, for example, near infrared 1 or 2. And to show this, I would like to bring up this plot, which illustrates an hyperspectral signature of grass with this black line, and also the same similar spectral signature of grass in both top of the atmosphere reflectance in blue and in red in surface reflectance. So these values have been calculating over 4 different cities, Honolulu, New York, Rio de Janeiro, and Istanbul, which represent different climates, different species, and the imagery will be a quite different season. For each of these lines correspond to either vigorous vegetation or stress vegetation. And what we can notice is that, as mentioned earlier, the Rayleigh scattering is particularly distorting the spectral shape of what we are measuring in top of the atmosphere reflectance, especially in coastal and blue band. We can see that this difference is it's quite real. Relevant. And the other spectral distortion that we can notice is in the near-infrared 2 band, and this is because around 940 nanometers of water vapor be well in agreement with the hyperspectral signature. It is because, again, there is more Rayleigh scattering, and this is the spectral distortion that we would like to correct using surface reflectance. So what are the advantages of using surface reflectance? So commonly the analysis of very high spatial resolution images has been limited only to the use of digital numbers, which as shown, they don't really accurately describe the observed targets, especially between various collections that have been done using different viewing geometries or under different illumination conditions or atmospheric conditions. And so the advantages of using surface reflectance are that it improves the performance of multitemporal data analysis and also facilitates the cross-sensor processing and enables the extraction of information using physical quantities. And this is particularly important when we need to analyze large archive of data and when the agility of the satellite might be a constraint. So in the first case, when we have large archive, we need to mention that the commercial availability of optical resolution images began more than 10 years ago with Igonos and QuickBird, and since then a large amount of data has been acquired, even with newer platforms such as Worldview 1, Worldview 2, and GeoEye. And currently the global capacity for very high spatial resolution images is about 1.8 billion square kilometers per year, which corresponds roughly to 12 times the land surface of the Earth. And this is expected to increase to more than 2.4 billion square kilometers per year, which corresponds to about 16 times the land surface in the near future. We have a big archive, and we need to be able to exploit this archive. As an additional example, this plot shows 30 days of collection by only QuickBird, Worldview 1, and Worldview 2. And so this, again, points out the fact that there is the need for robust automatic feature extraction techniques. Regarding the satellite agility, the Worldview class of satellites has a high-performance camera control system which is capable to rapid retargeting, allowing the collection of dozens of images within a few seconds. And so this is also particularly interesting because in case of emergency, the viewing geometries are usually opened up to maximize the collection opportunities. And to give you an example, I'm going to show you now a multi-shot sequence that we collected about 3 years ago over Rio de Janeiro. And this collection is composed by more than 30 shots. Again, they're being acquired in sequence. And you can appreciate that the lower the elevation angle is, the more the image looks bluish, like in this case now. That means that we are going through a longer path of atmosphere, and so the atmospheric effects are more important, and so we need to be able to correct for those effects. Another reason why we are particularly interested in surface reflectance is the fact that we are about to launch next year a new satellite, Worldview 3. And probably you already heard that Worldview 3 is going to have 8 bands that are going to be very similar to the 8 band of Worldview 2, but it also has 8 additional bands in the SWIR part of the region, so longer wavelength. So maybe not of you are aware of the fact that there's going to be another instrument called CAVIS on board of Worldview 3. CAVIS stands for Clouds, Aerosol, Water, Vapor, Ice, and Snow, and it was designed to retrieve atmospheric components that are necessary to then correct the images in surface reflectance. CAVIS has a 30-meter spatial resolution, and it will have 12 linear and SWIR bands. That makes Worldview 3 a 29-band satellite, including the panchromatic band. So what is, at this point, the importance of working with surface reflectance? How can I show you that? Well, what I decided to do was to create a time series data set. In this case, I use about 20 shots over Denver, Colorado between 2002 and 2009. And this image covers part of the downtown area of the city, including single-family houses or skyscrapers, but also roads and highways and urban parks and bodies of water. You can appreciate in this polar plot that the images have been acquired with fairly uniform spatial distribution in both zenith and azimuth, and the sun shows the declination through the year. For this dataset, we also collected 22 classes of interest, and we will see later more on these classes. What I want to point out is that those are not common classes. We are trying to define and discriminate 5 different types of grass, 2 different kinds of water, 3 different kinds of soils, and several different kinds of rooftops and parking lots. So this is not the standard land cover classification that most of the people are doing. So the first challenge that I have is I have these 2 images that have been acquired in 2002 and 2008. And can you count the number of relevant changes in less than 10 seconds? And most likely you cannot see how many changes took place in such a short time. So what people do usually is to create a computer-based program to do this. And one approach that it's commonly taken is to use principal components. I'm not going to go into the detail of the algorithms, but what I want to show is that if you use this approach and you use digital numbers, you end up with something like this. So again, you have a lot of false alarms and you don't really know where the relevant changes are. However, if you apply this exact same methodology by using Surface Reflectance as an input space, you get this kind of output, where now it's much easier to identify the 15 relevant changes. So you should think about this if you are an operator on the field and you are, for example, engaged with some rapid response. You want to have a map like this one instead of the other that I showed you previously. Another example I would like to show regards the multi-temporal spectral signature analysis. In particular, if I have this kind of plot where I have on the x-axis the dates of the acquisition, again they're between 2002 and 2009, we have on this y-axis the normalized DN, and normalized DN basically means that we are normalizing everything to be consistent with values that goes from 0 to 1 to be able to compare then those values to surface reflectance. On this other axis, we also have the aerosol optical depth, or AOD. The AOD is inversely in the inverse of the visibility. So the lower is the AOD, the higher is the visibility. So if I ask you now, what are we looking at? Probably we cannot really give an answer because there is so much variability through day to date that makes it impossible to understand what we are looking at. Maybe the only educated guess that we can do is that this object might be green because green is the highest of the visible bands. As you can see, blue and red are much lower than green. So the only educated guess that I can have is that maybe this object is green, but I can't really explain that variability. Instead, if we analyze the spectral signature in surface reflectance space, we can actually see now that there are three big plateaux of reflectances. In particular, between 2002 and 2008, we have about 35% reflectance, whereas this object got much darker between 2007 and 2008, and after 2008 got bright again. So we can probably still not explain what's going on, but we can now see that this object probably went through some change, some dramatic change through the years. And also now I'm not really sure anymore if this object is green because all the visible bands are actually quite close to each other. So I will probably say this object is some shade of gray. And sure enough, if I show the object, we can see and understand why there are these three big plateaus. In particular, the object went through some renovation through the years, and between 2007 and 2008, the roof was actually black. That explains why it was so dark here. And then after 2008, they changed the roof type, and with some material that was much brighter. Another thing that's really worth to mention is that the day-to-day variability of the digital number spectral signature is correlated to the IOD. So it's correlated to the visibility or to the atmospheric profile. And the correlation coefficient is 0.42, which is significant to the 5% confidence level. However, there is no correlation to the IOD in the surface reflectance domain. Again, we carry out this validation using a 5% confidence level. This emphasizes the fact that atmospheric conditions significantly affect the digital numbers input domain, and that's another reason why digital numbers should not be used to do image comparison. So if I show again this plot which represents normalized digital number, can you tell me what we are looking at? Probably not. Again, for the same reason I discussed with you earlier. There is a lot of variability through the years, and so it's really hard to say what we are looking at. Some educated guess may be that this material can be consistent with some natural surface. In particular, what I can notice is that the near-infrared is higher than the other bands in summer season, so that makes me think that probably I'm looking at vegetation. However, it's somehow strange to see that red is higher than green, and I mean, we are fairly confident vegetation should be green and not red. And so, to answer again what we're looking at, we should probably look at surface reflectance data as in this plot. So now what we can say is that the objects might not be actually vegetation, because I don't see any more increase in near-infrared values during summer season. And actually, I can probably say that this object is red because the higher value compared to the blue and green band. So again, I cannot really explain what it is. I just know that it's something that could be man-made and could be red. However, there is still some variability through the day-to-day acquisition. And so what I can say is that this variability is not correlated to the visibility. So this variability is something that is a feature of the material. And so to solve this mystery, we need not to look at multitemporal series only in the multitemporal domain, but also in the angular domain, as we are doing now in this plot, which is again, it's a polar plot. We show with yellow the position of the sun, and black are the position of the satellite during the acquisition. What I want to point out is that the variation goes from 22% to 24%, so it's a very, very small variation. But as you can see, it's a very consistent variation. In particular, this object seems to be much brighter, or consistently brighter from the east side, whereas it's darker on the west side. So there is a clear, consistent bimodal refracted distribution. And this kind of information is a structural information of the object. And what we can understand is that this object is most likely a pitched object. So there should be some pretty pitch component with this surface. And so I can show you now what this object was. And sure enough, was a red pitch roof. And so this demonstrates the fact that the angular information of the acquisition should not be neglected, as useful additional information can be extracted from it. But now one other question could be, okay, how can we exploit this information? And so during the years, a large number of techniques have been proposed to characterize and efficiently use angular information. For this slide deck, we use the so-called RPV model, and I put here the reference if someone is interested. And the characteristic of the RPV model is that it decomposes the angular observation into three independent components, namely the amplitude, the shape anisotropy, and the asymmetry factor. This also means that there is a data inflation. So if we start from quick wave bands, so from 4 bands, blue, green, red, and near infrared, we will obtain 12 input features because we have 4 bands times 3 additional decomposition. So we end up with a higher input space, which is usually what we would like to have. So we want to increase the input space to have a better training of our machine learning models. And to show this, I will go through a very simple example. As you remember at the beginning, I said that we had 5 different kind of classes on our Denver time series. And this is, again, the normalized DNA. You can see there is some big variation, which is the result of having a time series. From this kind of data set, it's really hard to discriminate between the various kind of grass. And by the way, what we did was to select 3 healthy vegetation cover and 2 less healthy vegetation cover. And so what we would like to have is at least 2 big clusters. So we would like to discriminate at least between healthy and less healthy vegetation. However, in this case, we only end up having 1 big cluster. So digital numbering doesn't really provide much discrimination power. On the other hand, if we use surface reflectance, we can notice that we have a reduction of the variability of the data set through this time series. So the box plot are smaller than this other one. And this allows us to create a better discrimination of the data set. In particular, we can easily select a line here about like 0.5 that discriminates between healthy and less healthy vegetation. Now, if we want to take this further and we want to be able to discriminate different kind of vegetation cover, we should also analyze the angular component of our data set. And to do this, as I say, we use the RPV model. So the first component is the amplitude, which is very closely related to surface reflectance, so the amplitude is surface reflectance. So it is not surprising that we can easily find a threshold here to discriminate between healthy and less healthy vegetation. Now, if you look at the second component, which is the shape anisotropy, we can now discriminate we can now detect two different thresholds, which will help us discriminate 4 different kind of grassy area in conjunction with the amplitude of the RPV model. And again, if we look now at the symmetry factor, we can discriminate, we can generate another threshold, and using this threshold and the other 2 pieces of information of the RPV model, we are now able to discriminate all 5 different kind of grass. And so again, we keep adding features. So we go from raw digital number to surface reflectance to angular decomposition. And to put this in a larger perspective, our 22 class urban land cover classification, what I'm showing here is the kappa coefficient of these classes, and you can see that we didn't get better than 48% accuracy using digital numbers. And what we can notice is that the grassy surfaces have a very low accuracy that ranges between 10 and 35%. So this is usually not acceptable. If you work in the surface reflectance domain, we can notice now that we have a fairly larger discrimination of the grassy area. Still, it is not a satisfactory result, but it's much better than the working with digital number. And what we can see is that now the overall accuracy in terms of kappa coefficient is about 0.71, and that represents an increase in accuracy of about 50% with respect to digital numbers. So only because you're working surface reflectance, you get about 50% accuracy improvement. Now, if you want to be more sophisticated and we also want to use angular decompositions, we can see that our overall accuracy jumped to 85%, which is an improvement over the base case of digital number of about 80%. And in this case, now we can see that the grassy areas can be well discriminated with all values being above 0.70, in particular between 0.71 and 0.92. And so again, using more sophisticated technique based on surface reflectance, we can increase the overall accuracy. So now one of the questions that people might have is, okay, surface reflectance is to be a pretty interesting technology, but how do we obtain surface reflectance? What is the technology that's available for the end user? So usually there are at least 2 big family of methods. The first one is basically a statistically based approach that look at the image, and based on the statistics of the image, it's able to retrieve some information which is relative to the atmospheric conditions. The other method, the other class of method is it's based on the first principles, and usually they are much slower to run, and we need to know what are the atmospheric conditions. However, those approaches are usually much more accurate. And so to do some analysis, what we use are Quark and FLAASH, which are implemented. They're both implemented into the MV software, distributed by XLSVs. And so Quark, it's a statistically based method, and that means that it's much faster compared to first principle methods. On the other hand, FLAASH is a first principle method based on Modron, and it requires the information of the atmosphere, but it represents also a very accurate method. DigitalGlobe has developed a fully automatic framework, we call it DigiAcomp, for atmospherically compensated very high spatial resolution images from QuickBird, WorldView 1, and WorldView 2. So our goal is now to validate DigiAcomp, and to do this we use 3 different approaches. We use in situ measurements from field spectrometer, and we also compare DigiAcomp retrieval to Quark and FLAASH. As said, Quark is fully automated as a DigiAcomp, and it represents the baseline to compare DigiAcomp with. On the other hand, FLAASH requires the knowledge of the atmospheric components. In particular, you need to know aerosol, water vapor, and quantities like this. But also, FLAASH represents the most accurate method that is currently available, or at least one of the most accurate methods. I want to also mention that in this presentation we drive FLAASH using the values that were automatically retrieved by DigiAcomp. Particularly the aerosol optical depth and the water vapor are the ones that they were provided by DigiAcomp. We have done 2 different kinds of validations. One uses time series over Longmont, Colorado, and the other one uses calibrated tarps. Let me walk you through the first example, the first experiment. We had about 50 images acquired between WorldView 2 and WorldView 1 and QuickBird between 2009 and 2012. And what we did was to go outside and measure directional reflectance. So basically we measure surface reflectance in a multi-directional way of concrete and asphalt. This material, concrete, it's a sort of like rough surface, whereas the concrete is a smooth surface, which because it's a basketball court. And this is actually important to mention because these 2 materials will have different structural components, and so also the angular information is different, and the angular characteristic is different. And this is why I mentioned that we took directional measurements with our field spectrometer. And what you can notice is that asphalt has a backward scattering property. In particular, the brightest side is the one that is facing the sun. And whereas for concrete, we have exactly the opposite behavior. So the brightest surface is the one that is away from the sun. One important thing I want to mention is that for this kind of analysis, we are assuming that the targets have constant in time spectral behavior. So the spectral behavior of the material doesn't change, which is actually not true because people play on the concrete field, or cars drive on the asphalt surface. And we also assuming that the illumination through the air doesn't change, which again is not really correct. Again, we are putting ourselves in the worst case scenario to do this analysis. This is the response of the field measurements, and you can see those box plots are the results of the different viewing angles of these 2 specific materials. This is the result using Quark. And what we can notice is that, first of all, Quark doesn't provide any information using the panchromatic band. So Quark must be used only on multispectral images. And also we can notice that the results are not very accurate. The root mean square error is about 0.09, so 9%. For concrete, and about 2.5% for asphalt. On the other hand, FLAASH, as expected, is performing very well, and you can see that there is almost no error compared to the field measurements. On the other hand, also FLAASH doesn't provide any retrieval for the panchromatic band. Finally, DigitalGlobe. As you can see, DigitalGlobe perform very similarly to FLAASH. And also the root mean square error between the two methods is very comparable, is about or less than 1% across all the bands. And also you can notice that the panchromatic band has been retrieved. And I want to point out that the panchromatic band and the multispectral band produces two completely different outputs. So those are two completely different kind of retrievals, and yet they're both fairly accurate. The other comparison and the other analysis we have done has used calibrated tarps, and those those tarps are manufactured to guarantee flat spectral responses between 400 and 1,000 nanometers. And if you want to have more details about those tarps, you can get more information from those two papers. In particular, what I want to point out is that we have 4 calibrated tarps at 3.5, 22, 34, and 52% reflectance, and we have about 12 images acquired across the US at different times. Again, this is the result using Quark, and we can see that it doesn't seem to perform very well. We would like to see the 52% retrieval along this line. Instead, it doesn't really perform well, and also the box plot is quite wide, which means that the results are not very consistent. On the other hand, again, FLAASH seems to be working very well. We have here the 52% TARP, the 34, 22, and 3.5 reflectance TARP. So it's not really a big surprise. FLAASH, again, works very well. But on the other hand, also, DigitalGlobe seems to be performing very well. And again, I'm showing both retrieval at the same time, and you can almost not notice any difference. So that means the DigitalGlobe seems to perform as well as a FLAASH. So how can the user get access to the DigitalGlobe Surface Reflectance product that is being generated by DigitalGlobe? So we have established an alpha program, and so basically DigitalGlobe is validating this technology now with customers and partners. And so if you are interested in learning more about the product or interested in participating in these paid trials, I would suggest you to write me an email at fabio.pacifici@digitalglobe.com, and I can provide you more information. Since we have a few more minutes, I would like to show you some other application that Surface Reflectance can bring on the table. The first one is image enhancement. Let's say that we have this image that was acquired by QuickBear a few years ago. As you can see, there is a very variable, very non-uniform maze through the image, and the image doesn't really look appealing. Our method is able, as say, to retrieve the visibility of the scene. And once we have this kind of information, we can feed it to DigitalGlobe to get a result like this one. Now, color seems to be more balanced, and most importantly, most of the haze has been cleaned up. Another application is biophysical information of vegetation, for example. These kind of quantities are very important for climate and ecological models. One of the simple indicator of chlorophyll content is the NDVI, so it's, which stands for Normalized Difference in Vegetation Index. The NDVI is very easy to calculate. It's basically the ratio between the near infrared and one of the visible bands, which usually is the red band. This NDVI value goes from -1 to 1, and positive values are usually an indication of vegetation. Particularly if the NDVI is higher than 0.2 or 0.3, it's an indication of healthy vegetation. In this plot, what I'm showing is, again, an aerospectral signature of grass that we acquire with our spectrometer. And we also illustrated with these blue triangles the top of the atmosphere reflectance, and with red the surface reflectance. So if you calculate NDVI from top of the atmosphere reflectance, you get this quantity, so around 0.8. Whereas you can see that the actual NDVI should be around 0.9. According to this hyperspectral signature. So if you don't use surface reflectance, you are committing about 10–15% error. To illustrate this visually, we can plot the NDVI values and in both digital numbers or top of atmosphere reflectance in this case, and surface reflectance. So what can be noticed is that those two fields, which correspond to those two, seems to have different level of vigor. So this one in particular seems to be more stressed than the other one. However, this is just a spectral distortion of the atmosphere. In fact, if we reanalyze our data using surface reflectance, we can now notice that those two fields have very similar NDVI values, even though the RGB color seems to be quite different to each other. And once you have better NDVI estimate, we can also, for example, estimate the leaf area index or other biomass variables. Another example I want to bring up is oil spill mapping. In particular, this was an example from the oil spill over the Gulf of Mexico a few years ago. And what you can notice is that the top of the atmosphere radiance seems to be having a trend that's completely different from the surface reflectance. In particular, this is decreasing with wavelength dependency, whereas this is increasing. So which one is correct? Well, to help us out on this, we use some spectral libraries from USGS of oil, in particular oil spill. And we can see that using matching techniques that our surface reflectance curve seems to be more in agreement with this plot. And actually, using this information, we can say that that specific point had a concentration of oil of about 25%. So this kind of information is actually really helpful because we can now create oil spill maps. How do we do this, and how do we compare it? Well, the easiest thing to do is to use as a comparison tool SAR images. SAR is very good to retrieve oil spill because of the suppression of the capillary waves of electromagnetic signals in the presence of oil. So the community has been usually using SAR techniques or SAR information to extract oil spill. However, we can provide the same kind of information as shown here in these maps. Again, these are probability map of presence of oil. And one thing I would like to show you is that you can see here, this is higher concentration of oil. And this is a kind of information that you cannot get using SAR systems. Here everything looks black. So if you have to send first responders, you don't actually know where to send them, where is the highest concentration of oil. Whereas using optical sensor, you can actually understand where the higher concentration of oil is. And I can zoom in this area, and this is the kind of information that you can extract. So you can see that here there is a higher quantity of oil, and this is the mapping of this surface. So to conclude this webinar, surface reflectance is a fundamental technology that is necessary for extracting information from imagery in a reliable way over a large area, and with the imagery collected over a large period of time. Its applications are countless, and they include uncover and reuse, change detection, large mosaicings, environmental studies using, for example, NDVI, leaf area index, or biomass, and also oil spill mapping, target detection, or bathymetry. So I'll say these are fundamental technology. It's a base layer that people should be using to build other products on top of it. I want to mention again that we are looking for alpha customer, and I'll thank you for your attention.
So thank you, Fabio, for your informative presentation. At this time, we'll now open the Q&A portion of the webinar. Please type your questions into the chat box feature that's located at the right-hand side of your screen, and we'll answer the questions in the order that they're received. So I'll give everyone just a couple of moments to begin typing in your questions. So Fabio, I have your first question for today's webinar, and a listener is asking, do you use DOS, which is dark object subtraction, while calculating surface reflectance?
Okay, so the dark object subtraction is one of the many techniques that have been used in the literature. I don't really want to get into the details of our algorithms for IP issues. But what I can say is that our method does not rely on the presence of dark pixel. However, if we have dark pixel in the scene, then those kind of objects can be taken into account to have an independent source of information.
Another question that came in is someone is asking, how long do you expect before this is going to be made as a commercial offering?
So we are establishing now the alpha program. We need to work with customer and partner to make sure that the product is up to their quality requirements. I believe that at the end of the alpha program, we should be able to start selling the Surface Reflectance product. I would assume it's going to be sometime the end of this year or early next year.
Another listener is very interested in what you had to say about becoming an alpha customer, and they're wanting to know if you have any more information to share about that.
I would say the easiest thing to do is just to write me an email, and I can touch base with this user, and I can provide more information to them.
So we'll give everyone just another moment to type in their questions. So Fabio, another question that has come in for you is they're asking, does your surface reflecting algorithm work on other satellites, like a Landsat 8 or a Pleiades? And if the answer is yes, what are the advantages with our technique?
Okay, so we did not test the JComp on these satellites yet, but I believe that the technology behind our algorithm is capable to process both Landsat 8 and Pleiades datasets. So as shown during the webinar, the JComp was able to successfully run even on just the panchromatic image, just the panchromatic band of WorldView 2. So that means that I do not anticipate any problem using either of those two satellites this user mentioned. Regarding the advantages, well, I mean, first of all, DigitalGlobe is fully automated, which means that there is no human in the loop. It runs on the HPC, which again means that it can be processed a standard WorldView 2 scene in less than a minute. So it's very fast and completely automatic. It can be satellite independent, so we can process other satellites datasets. And another thing I can add is that DigitalGlobe was specifically developed for very high spatial resolution images. So other techniques might not be taking care of the differences in spatial resolution.
Another question from a listener is they're asking, what does a surface reflectant product delivery look like?
So the surface reflectance product will look like very similar to the current product. So instead of delivering digital numbers images, So digital number usually goes from 0 to 2047. We have 11-bit quantization. So instead of having those digital numbers, the user will get values that they can be either 32-bit floating point that range from 0 to 1, which is the common surface reflectance scale, or we can also provide 16-bit integer, which are smaller in size, and for example, the range could be between 0 and 10,000.
And your last question for the webinar is, a listener is asking, can you process archived data with this technique?
Yes, that is actually one of the main goals of Surface Reflectance. So we want to be able to normalize all the data that we have to a common denominator. So if you have like a big archive, it will highly encourage people to order Surface Reflectance, because then you can compare your old image with a newer one, and that Surface Reflectance make it easy to do this comparison.
So that's going to wrap up the Q&A portion of today's webinar. Thank you again, Fabio, for your informative presentation, and thank everyone for attending today's webinar. If you would like more information, or if you have additional questions for Fabio, please feel free to contact him directly. I have listed Fabio's email address on the slide. Also, a link to today's webinar recording will be sent to everyone within the next 24 hours. That's going to conclude today's webinar, and I thank you for attending, and we hope to see you at future events.